Hello everyone, and welcome to this video on Qr Factorization. In this video we'll learn what it means to take a matrix, an m by n matrix, and express it as a factorization Q times R, where Q is a matrix of the same size, an m by n matrix with orthonormal columns, and R is an upper triangular matrix. And the reason for this factorization, there are many applications that involve the use of this factorization that I won't be getting into in the video. But just know that there's a reason, there are many useful reasons to have this a QR factorization for an m by n matrix. And we're only going to specifically look at specific types of m by n matrices, something with a certain condition, as we'll see here. Alright, so if A, so capital A, is an m by n matrix, so m rows, n columns, with independent columns. I'll double underline that. That's the key, alright? So we look at an m by n matrix with, all n columns being independent, or we could say the rank of A was n. Remember, the rank of A was the number of independent columns or the number of independent rows, and those were the same number, right? The number of pivot columns or pivot rows. So if A is an m by n matrix with rank n, has all independent columns, then A can be expressed as the product, A equals Q times R, right? Thus the name QR factorization, right? The product of a matrix Q times a matrix R, where the matrix Q is an m by n matrix, so Q has the same size as A and has orthonormal columns. Right, so the columns of Q will form an orthonormal set, meaning that they're pairwise orthogonal and all unit vectors. And this matrix R is a square matrix, is an n by n matrix, right? Because an m by n times an n by n would give me an m by n. Right? R is a square matrix that is upper triangular. Remember, upper triangular meant all of the entries below the main diagonal were 0. Right? And if there are any non-zero entries, they're on the main diagonal or above it. Alright, so how do we find these things, right? How do we go about finding this matrix Q and matrix R? So the columns of matrix Q can be found using that Gram-Schmidt process. Remember the Gram-Schmidt procedure for taking a set of n independent vectors and creating an orthogonal set, and after that, you can normalize the vectors, create an orthonormal set of n independent vectors. So the columns of that m by n matrix Q can be found using the Gram-Schmidt process on the columns of A. And I said earlier, all the columns of A have to be independent to do this. So the columns of A must form a basis for some subspace of Rm, some n-dimensional subspace of Rm. And then to find R, just find Q transpose times A, because you'll know what Q is after you perform the Gram-Schmidt process to get a set of orthonormal vectors to form Q. You'll know what Q is, so then you'll know what Q transpose is, and you'll have A already. So yeah, R, that upper triangular matrix I mentioned, is Q transpose times A. Right. And the reason for this, because we're eventually going to express A in this QR way, right? The QR factorization. And Q has orthonormal columns. If a matrix has orthonormal columns and you multiply it on the left by its transpose, so if I multiply on the left by the transpose of Q, since Q has orthonormal columns, Q transpose times Q will be the n by n identity matrix. I n by n. Right. But be careful, not the other way around. Right? Q is only going to have orthonormal columns, not necessarily orthonormal rows. So Q transpose times Q will be the n by n identity matrix. But Q times Q transpose may or may not be the m by m identity matrix, but we're not relying on that. We're relying on this fact, that if Q has orthonormal columns, then Q transpose times Q will be the n by n identity matrix. And so I'm left with R equals Q transpose A. Right. All right, and I'll show you a demonstration of this later too. Right, that if a matrix has orthonormal columns, its transpose times it will give me an identity matrix. All right, and that's all. All right, it's really short and sweet. You just have to recall what that Gram-Schmidt process was, which I've done several times in previous videos. So hopefully you've been watching, following along. I'm going to do it again here several times. All right, so for the rest of the video, I'm going to be given a matrix A that has independent columns already. Okay. Now you can verify that all the columns are independent by putting it in reduced echelon form or just echelon form, and seeing that every single column will be a pivot column. All right. So you could verify that for yourself if you wish. But I'm going to say right now that I know they're independent. I'm given a matrix with independent columns. All right. So I'm going to start with a square matrix. Then we're asked to find the Qr factorization of A. Right. So I wish to write, I'll write it one more time here. I wish to write A as a product of Q and R, where Q has orthonormal columns and R is an upper triangular matrix. All right. So here I have a matrix with this is a 3 by 3, and it's a 3 by 3 matrix. And I already told you that all columns, you can check if, like I said, you can check if you want, but all columns are independent, right? So the rank of A, the number of independent columns, and therefore the number of independent rows is 3. So I should be able to write a QR factorization for this, right? Every column is independent. And every row as well, right? Just for, because this is a square matrix. We're going to see examples after this where my columns are independent, but the rows are not. All right, and I'll point that out, right? So we have every we have independent columns, right? That's key, right? Now I say, hey, I got independent columns. I can express this as some Q times R, where again Q has orthonormal columns, R is upper triangular. All right, so how do we find Q? All right, so that'll be my first part, right? Find this Q. So like I said on the earlier page, look at the columns. All right, so I'll call this, say this vector A1, all right, because it's matrix A. I'll call this vector A1, 1, 1, 0. This vector A2, 1, 2, 0. And this vector A3, 0, 1, 2, and all three of these are, this is a set of linearly independent columns, right? The set with vectors a1, a2, and a3 is independent, as an independent set, but it's not orthonormal, and we're going to talk about orthonormal under the dot product. All right, I know that there are other inner products out there, but we're going to use the standard inner product here, the dot product. So it's independent, right, but not orthonormal. So what I'm going to do is use that Gram-Schmidt procedure to construct an orthonormal basis, or an orthonormal set. Right. So I'm going to use Gram-Schmidt. All right, so remember how that worked. What are we trying to do with the Gram-Schmidt process? So I have an independent set of vectors, and I'd like to construct an orthonormal set of vectors. So here's how that worked, right? We're trying to construct, well, first I'll start with constructing an orthogonal set of vectors, and then we'll just normalize, right, the vectors, divide each vector by its norm. So I'm going to construct an orthogonal set first, where every pair of vectors is orthogonal, right? Every pair of vectors has a dot product of 0. All right, so I called these vectors a1, a2, a3. How about I call these vectors b1, b2, and b3? Why not? All right, so how'd this go? So remember, for the first vector in the orthogonal set, b1, I just chose the first vector from my original independent set. So b1 is the same as a1, so the vector 1, 1, 0. Okay, the vector 1, 1, 0. Then for the second vector in the orthogonal set, I took the second vector from the independent set, the original set, a2, and then subtracted the projection of a2 onto all the previous vectors in my orthogonal set. So minus the projection of a2 onto b1. Right, and that was the only previous vector in the orthogonal set that I've established. So I'm only subtracting the one projection here. All right, so what was a2? a2 is the vector, the second column here, 1, 2, 0. Minus, and then how do we do vector projection, right? The projection of a2 onto b1, it's just going to be a scalar multiple of b1, right? So I'll write down the vector b1, so that's 1, 1, 0, right, b1. And what's the scalar? Now remember, the numerator of the scalar is simply the inner product, or in this case, the dot product of a2 with b1. So a2 is 1, 2, 0. b1 is 1, 1, 0. The dot product would be 1 plus 2 plus 0. So 3 for the numerator. And then the denominator of the scalar is the dot product of b1 with itself. So 1 plus 1 plus 0. So 3 halves. All right, so 1, 2, 0 minus 3 halves times 1, 1, 0. And putting these together, I'm getting b2 is 1 minus 3 halves. That'd be 2 halves minus 3 halves. That's negative 1 half for the first component. Then 2 minus 3 halves. That's 4 halves minus 3 halves. That's positive 1 half for the second component. And then 0 minus 0, 0 for the third. And if you'd like, these all have like a half in common. That's half of the vector negative 1, 1, 0. Right, and check it out, right? These are orthogonal, right? If you did the dot product of 1, 1, 0 with negative 1, 1, 0 or negative 1 half 0, just a scalar multiple of it, you're going to get 0. These are orthogonal. Okay, and then for B3, I do the same thing just with just more subtraction, more projection subtraction. So for B3, the third vector in my orthogonal set, right, I take the third vector from my independent set, right, A3, and then I subtract the projection of A3 onto each of the previous vectors from the orthogonal set. So minus the projection of A3 onto B1 minus the projection of A3 onto B2. Okay. Alright, so working through this, A3, like I said, is the vector 0, 1, 2. That was the third vector in my set of independent columns from matrix A. So here's 0, 1, 2 minus, and then we're doing a projection onto B1. So it's going to be just some scalar multiple of B1. B1 was 1, 1, 0. And what is that scalar? Right? The numerator is B1 dot A3. So 0, 1, 2 dot product with 1, 1, 0. That's 0 plus 1 plus 0. So just 1 for the numerator of the scalar. Alright, and then for the denominator, it's B1 dotted with B1. So 1, 1, 0 with 1, 1, 0. That's 1 plus 1, that's just 2. So I got half of B1 is the projection of A3 onto B1, half of B1. Minus, and then a projection of A3 onto B2. So I'm going to have a scalar multiple of B2. Well, I'm going to write B2 this way. So here's half of negative 1, 0, 1, 0. Right, this was B2 times a scalar. Right, and again, the numerator of the scalar is the dot product of B2 with A3. So what's the dot product of 0, 1, 2 with this half of negative 1, 1, 0? Well, that would just be half of the dot product of 0, 1, 2 and negative 1, 1, 0. So, 0 plus 1 plus 0. So it's 1, but then times a half. So I got a half up here, right? Half in the numerator. So that's going to actually cancel. Oh, actually, no, that's going to make a fourth. All right. Then the denominator is the dot product of B2 with itself. So that's going to be a quarter plus a quarter. That's 2 quarters or a half, right? Or half of, this is this dot itself. So it's a half of this dot, half of this. So a quarter of 1 plus 1, a quarter of 2, that's a half. Right. So that so the projection of A3 onto B2 is just B2. It's just B2. Okay, wonderful. And then let's put all this together. So the halves here I don't really need. Right, a half divided by a half is just 1. And then putting this stuff together, we get our third vector in the orthogonal set that we're trying to create. Alright, so B3 equals first components. You have 0 minus a half plus a half. Alright, 0 minus a half plus a half. That's 0. Then second component, 1 minus a half minus another half. That's 0 again. 1 minus a half minus a half. And the third component, 2 minus 0 minus 0 is 2. Wonderful. Okay, so I have my orthogonal set. Alright, we're not done yet. We're trying to make an orthonormal set, right, for the columns of that matrix Q. So my orthogonal set is the set of vectors 1, 1, 0. And then B2 was that negative 1/2, 1/2, 0, and then B3, 0, 0, 2. And then all I need to do now is normalize these, right, to make an orthonormal set. Make all of these into a unit vector under the dot product. Alright, so remember the norm of a vector was the square root of the dot product with itself, or the inner product with itself. So the norm of this first vector is the square root of 2. Alright. So I just divide that vector by the square root of 2. And let me write down here, we're constructing an orthonormal set. Not working out with the colors here. So yeah, so we have 1 divided by the square root of 2, 1 divided by the square root of 2, and if you want to rationalize those you can, and then 0 divided by the square root of 2. Okay. The norm of this second vector would be a quarter plus a quarter, and then the square root of that, right? Well, a quarter plus a quarter, it's the square root of 2 over 2, right? A quarter plus a quarter is a half, and then the square root of a half, is the square root of 2 over 2. So if I divide these by the square root of 2 over 2, that's the same thing as multiplying by 2 over the square root of 2, which would cancel the 2's and give me square roots of 2's in the denominator. Right? So I have negative 1 divided by the square root of 2, positive 1 divided by the square root of 2, and 0. Right? And again, so far so good. Right? These are orthogonal, these two, and they're both unit vectors now. And then the third one, just 0, 0, 1, right? Its norm is 2, clearly, the square root of 4. Dividing by 2, I get the vector 0, 0, 1. Great. And I guess I'll call these vectors Q1, Q2, and Q3 because I'm going to, these are going to be the columns of that matrix Q that I want to find. Alright, so matrix Q with the orthonormal columns, and again, the matrix Q is going to have the same size as the matrix A, right? Matrix A is a 3 by 3, so matrix Q should also be a 3 by 3 when I'm done setting it up. And it's these made up of these three, orthonormal columns: 1 over the square root of 2, 1 over the square root of 2, 0, and negative 1 over the square root of 2, 1 over the square root of 2, 0, and then 0, 0, 1. Okay, so I'm not done yet, but I'm just going to put this in a bubble. Alright, this is half the battle. Alright, and now I wanted to show you that, when I take Q transpose, this is actually an orthogonal matrix. It's a square matrix with orthonormal columns. And the rank, we said the rank was 3. It has 3 independent columns and also 3 independent rows. All right, this is actually an orthogonal, what's called an orthogonal matrix. So that means that Q transpose is the same as Q inverse. That's what it means for a matrix to be orthogonal, right? Its inverse is its transpose. And I leave that to you to verify. All right, take Q transpose, multiply it by Q on either side, not just the left, and you'd get the identity matrix. All right, and like I said, we're going to see an example or two coming up where only the columns are independent. Right? The columns are orthogonal, not the rows. And if the columns are the only orthogonal set, then if you multiply by Q transpose on the left only, will you get an identity matrix? You'll see that in my next example. Okay, so I've got matrix Q, and then as I mentioned, to find that matrix R, I simply multiply on the left by Q transpose. All right. So R is Q transpose A. So I've got Q here. And let's now find R. Right. So that was step 1, find Q. Step 2, find this R, which again is going to be Q transpose times A. So I can do this one by hand. This is only 3 by 3. They're not that big. So Q transpose, the first row becomes the first column, right? So 1 over root 2, negative 1 over root 2, 0. And second row becomes second column, 1 over root 2, 1 over root 2, 0. Third row becomes third column, 0, 0, 1. So there's Q transpose, right, times A. Let's see, what was A again? Matrix A was this one here with the 1, 1, 0, 1, 2, 0, and 0, 1, 2. Alright, so there's Q transpose times A, and let's see what we get. Right, so it's a 3 by 3 times a 3 by 3, right? The result will be another 3 by 3. And if I did everything correctly, remember I said earlier, this matrix R is going to be upper triangular, meaning all the values below the main diagonal will be 0. All right. Okay. That has to do with the fact that these rows are now orthogonal to to columns with with different numbers. So row 1, well, with columns with numbers less than it, right? So like row 2 should be orthogonal the way I've set things up to column 1 of this matrix, and row 3 of the Q transpose should be orthogonal to columns 1 and 2. All right, again, that's through this Graham-Schmidt process, the way things are set up. So you're going to see that when I'm done here, R is going to be upper triangular. All right, so first row, first column is 1 over root 2 plus 1 over root 2 plus 0. That's 2 over root 2, or just the square root of 2. All right, 2 divided by the square root of 2 is just the square root of 2. And then first row, second column, 1 over root 2 plus 2 over root 2. That's 3 over root 2. Then first row, third column, just 0 plus 1 over root 2 plus 0. That's 1 over root 2. All right, then second row, first column, negative 1 over root 2 plus 1 over root 2 plus 0. That's 0, as I was hoping, right? Again, it's going to be upper triangular. All the values below the main diagonal will be 0. They should be. Then second row, second column, negative 1 over root 2 plus 2 over root 2 is positive 1 over root 2, right? Plus 0. Then second row, third column, 0, 1 over root 2, 0. So 1 over root 2 again. All right, then here we go. We should get zeros here and here. Let's see. Third row, first column, 0 plus 0 plus 0. Hey, hey. And then third row, second column, 0 plus 0 plus 0. Look at that. This is an upper triangular matrix. And then third row, third column, 0 plus 0 plus 2. And look at that. Right, look at that. That's nice. That's what I wanted. Upper triangular. As we hope for. Okay. So I leave this to you. You can verify this on your own. Now that I have the matrices written, you can verify that A, okay, matrix A was this 1, 1, 0, 1, 2, 1, 0, 0, 2. Verify that that's equal to Q times R. Right, so Q, remember, was this matrix, this 3 by 3. Multiply this matrix by this matrix, and you'll get A. Right. In fact, I'm going to pause the video, and I'll just enter those into my calculator and show you that the result is true. Okay, we're back, and I entered into my calculator. All right, matrix A you're seeing on my screen, that's matrix Q. I entered these numbers in a 3 by 3 matrix. Matrix B on my screen is matrix R, this 3 by 3 matrix, this upper triangular matrix. And you see that Q times R, which on my screen is A times B, is the matrix 1, 1, 0, 1, 2, 1, 0, 0, 2. That was matrix A, see? So we do indeed have A equals this matrix with orthonormal columns multiplied by this matrix that's upper triangular. Great. We have found the Qr factorization. All right, so let's do that again. I got a couple more examples. That first one was a square matrix. All right, the first example was a square matrix. Just know that it doesn't have to be a square matrix to be able to have a QR factorization. All right, just so long as the rank is the same as the number of columns, right? Just so long as the number of columns is all the columns are independent, you can write a QR factorization. So here is a 3 by 2 matrix. 3 rows, 2 columns. So I'm asked to again, and again, I'm telling you, and there's only 2 columns here. You can see they're independent. Right, the rank would be 2. Right, the rank of A is 2. You have 2 independent columns. They're not scalar multiples of each other. But notice how the columns are independent, but not the rows. Right, remember, if the number of vectors is greater than the number of components in each vector, it's going to be a dependent set. So I've got 1, 1, 0, 1, 1, 0. That's 3 vectors from R2 that make up the rows. That won't be an independent set. So the columns are independent, but the rows are not. Right? In fact, if you took the first row minus the second row, you'd get the third row. Right? They are dependent. You can write one as a linear combination of others. All right, but the columns are independent, so I should be able to still do this. I should still be able to express A as a matrix Q times a matrix R, where again Q has orthonormal columns and R is upper triangular. Right? So first I'm going to find Q, just like last time. Find that Q using the Gram-Schmidt process. Alright, so like I did with the last example, these the 2 columns are independent, right? Don't worry about the rows this time. Column 1, the 1, 0, 1, I'm going to call that vector, since it's matrix A, I'll call this A1. And the column 1, 1, 0, that vector, I'll call A2. So we have an independent set of vectors with vector 1, 1, 1, 0, 1, A1, and 1, 1, 0, A2. I'm going to perform that Gram-Schmidt procedure because this is not an orthogonal set, so definitely not orthonormal. Because look at the dot product of 1, 0, 1 with 1, 1, 0. The dot product of these 2 vectors is 1, not 0. They're not orthogonal under the dot product. So I'm going to apply the Gram-Schmidt procedure to make construct an orthogonal set, and then we'll just normalize the vectors, right? Divide each vector by its length, its norm, to get an orthonormal set, and we'll have our columns of Q. And remember, the size of Q will also be a 3 by 2 matrix, so it'll be the same size as A. And then R would have to be a 2 by 2. Right? And it's going to be an upper triangle, and we'll see all that coming up. All right. So I'm trying to create, let's make an orthogonal set first. make an orthogonal set, say with vectors b1 and b2. Alright, so just like last time, remember how that goes. b1, the first vector in this orthogonal set, is simply going to be, just take the first vector from the independent set. So b1 is a1, alright, this vector 1, 0, 1. And then the second vector from the orthogonal set, b2, is just, a2 minus the projection of a2 onto the previous vector from the orthogonal set. Well, there's only one previous vector, so just onto b1. Okay, so this would be a2. a2 is the vector 1, 1, 0. Minus, and when I project on the b1, I'm getting a scalar multiple of b1, so a scalar multiple of 1, 0, 1. And what is this scalar? The numerator is the dot product of b1 with a2, right? So the dot product of these two vectors, I already mentioned that that's 1, divided by the dot product of b1 with itself, which would be 1 plus 0 plus 1, which is 2. Alright, so minus a half of 1, 0, 1. So that second vector in an orthogonal set I'm trying to construct is the following. So 1 minus a half to half. And then 1 minus 0, 1, 0 minus a half, negative half. Right? And if you'd like, I'm going to pull the half out here. This times the vector 1, 2, negative 1. There's the second vector in this orthogonal set. All right, and then all I have to do is normalize them, right? Divide by their norms to create an orthonormal set. And these orthonormal vectors will form the columns of that matrix Q that I'm looking to create. So let's make an orthonormal set of vectors by just normalizing them. So what's the norm of 1, 0, 1? That'd be the square root of 2. So let's divide each of these components here by the square root of 2. 1 divided by the square root of 2, 0 divided by the square root of 2, and 1 divided by the square root of 2. Okay. The norm of b2 is just half of the norm of this vector. The norm of 1, 2, negative 1 would be the square root of 6, right? 1 plus 4 plus 1. The square root of 6, and then half of that. So square root of 6 over 2. The norm of b2 is the square root of 6 over 2. So I'd multiply by 2 over the square root of 6, right? The reciprocal. Well, that'll get rid of this half, and then just put the square root of 6 underneath all these components. So it's going to be 1 over the square root of 6, 2 over the square root of 6, and negative 1 over the square root of 6. And there you go. There is an orthonormal set of vectors, right? They do the dot product of both of them, you get 0. Right? The dot product of the pair. They're orthogonal, and they are both now unit vectors under the dot product. So again, I'll call these Q1 and Q2. Right, these are going to be the columns of that matrix Q I'm trying to find, that matrix Q with orthonormal columns. So the matrix Q is a 3 by 2, same size as A, where the first column is 1 over the square root of 2, 0, 1 over the square root of 2. Second column, push that up a bit, 1 over the square root of 6, 2 over the square root of 6, and negative 1 over the square root of 6. All right, and again, only the columns are orthonormal, not the rows, right? If you looked at the rows aren't unit vectors. The rows do not form an orthonormal set. They're not even independent. It's only the columns. So you're going to notice that if you took Q transpose times Q, right, this is that'd be a 2 by 3 times a 3 by 2, you would get the 2 by 2 identity matrix, right, which I'll call I2, right, I sub 2, 2 by 2 identity matrix. But right, again, that's only because the columns are orthonormal. The rows are not orthonormal. So if you tried Q times Q transpose, this would not be the 3 by 3 identity matrix. And try it out. Again, I leave that to you to verify. Right. And we don't really worry about this one anyway, right? I'm not worried about Q times Q transpose. I'm worried about Q transpose times Q, right? Because I want to take this equation up here, and in order to find R, I would multiply by Q transpose on the left. So the only one I care about is this. And if the columns are orthonormal, Q transpose times Q will be, in this case, the 2 by 2 identity matrix. So that gives me R equals, Q transpose times A. Right? So let's find that R. Let's find that matrix R, and again, it's the way to find it is after I've found Q here, and I'll put this in a little box, a little bubble. I'm not done, but it's half the problem. Then I want to find, Q transpose times A. All right, so Q transpose is a 2 by 3, right, where you have 1 over the square root of 2, 1 over the square root of 6, 0, 2 over the square root of 6, 1 over the square root of 2, and negative 1 over the square root of 6. Right, there's Q transpose times, and then matrix A. Right, matrix A was that 3 by 2 again. Right, with the 1, 1, 0, 1, and 1, 0. And again, if I did everything correctly, and I'm pretty sure I did. I don't think I made any arithmetic errors, but if this doesn't work out, I'll go back and try to find it. This should result in an upper triangular matrix. Right, and then I'll go to the calculator and verify. I'll check my solution. All right, now it's a 2 by 3 times a 3 by 2. So this is going to be a 2 by 2 matrix. So first row, first column, be 1 over root 2 plus 0 plus 1 over root 2. That's 2 over root 2, but 2 divided by the square root of 2 is just the square root of 2. And then first row, second column, you just got 1 over root 2 plus 0, so 1 over the square root of 2. All right, now this should be 0 if this is going to be an upper triangular matrix. All right, every entry below the main diagonal should be 0. Let's see. Second row, first column, you have 1 over the square root of 6 plus 0 plus negative 1 over the square root of 6. That is 0. Hooray. This is going to be what I want. This is going to be an upper triangular matrix. And then second row, second column, dot product here, you got 1 over root 6 plus 2 over root 6, right? That'd be 3 over root 6, and then plus 0. So 3 over the square root of 6. There's R. All right, so there's the other half of my Qr factorization. All right, and then what I'm going to do is go to the calculator again. I'm going to pause it and just show you the result. I'm going to verify to myself that indeed matrix A that I was given is equal to that matrix Q with the orthonormal columns times this matrix R, which was this upper triangular matrix. All right, so I'm going to enter this matrix, right, a 3 by 2, and this matrix, a 2 by 2, and multiply them and see that we get 1, 1, 0, 1, 1, 0 back, right, matrix A. All right, so I'll be back in a flash. Okay, and I'm back now, and I've entered, now I just replaced again here matrix A on my calculator. All right, where you see an A times B here. Matrix A, I entered this 3 by 2 matrix Q as you see it here. And the matrix B on the calculator that you're seeing, I entered this 2 by 2 matrix, this R. and you see the product of them, Q times R is matrix A, is 1, 1, 0, 1, 1, 0, and it works out. All right. Okay, so I've got just one more example. All right, like I said, as long as the columns are independent, as long as all the columns of a matrix are independent, you can write this Qr factorization. So it doesn't have to be square, right? So here's one last example where it's not a square matrix, and I want to write the Qr factorization. And again, now there's 3 vectors here, 3 columns. If you want to verify that they are indeed independent, you can put this into echelon form or reduced echelon form and see that each column will contain a pivot. All right, each column will be a pivot column. All right, so the rank, we'll say the rank is 3, right? Now this is a 4 by 3 matrix, right? The 4 by 3 matrix. But the rank, the rank is 3. All 3 columns are independent. Obviously, right? Obviously, the rows are not independent. Because look, the second row and the third row are exactly the same vector from R3, right? So the columns are independent, but the rows are not. But all that matters to me to be able to express this matrix as a this QR factorization again is that the columns are independent. All right, so again, I want to write this. I want to write A as Q times R, where Q has orthonormal columns and R is upper triangular and in fact equal to Q transpose times A. All right, so I'll start off again by finding that Q using that Gram-Schmidt procedure. All right. So just as with the last examples, all 3 columns here are independent. First column with the 4 ones, 1, 1, 1, 1, I'll call vector A1. Second column with 0, 2, 2, 0 is vector A2. And the third column with negative 1, 0, 0, 0, A3. All right. So again, first I'm going to form an orthogonal set from this independent set of 3 vectors. Let's call them B1, B2, and B3 again. And as before, just let B1, the first vector in my orthogonal set, just be the first vector from the independent set. So B1 is A1, so just the vector with 4 ones, right? 1, 1, 1, 1. Okay, then B2 is A2 minus the projection of A2 onto B1. All right, so A2 is that 0, 2, 2, 0 minus, and when I project onto B1, right, I'm just getting a scalar multiple of B1. All right, the numerator of that scalar is the dot product of A2 and B1. That would be 4. And then the denominator is the dot product of B1 with itself. Well, that would just be 4 as well. So it's just 0, 2, 2, 0 minus 1, 1, 1, 1. So my second vector in the orthogonal set is 0 minus 1, negative 1, 2 minus 1, 2 minus 1, and 0 minus 1. All right, and you can check, look at B2 and B1. They are orthogonal, right, under the dot product. When you take the dot product of these 2 vectors, you get a dot product of 0. They are orthogonal. All right, and then the third vector. All right, this is like my example earlier with the 3 by 3 matrix. There were 3 columns. Same thing here, 3 independent columns. my third vector, say B3, from the orthogonal set I'm trying to create. I take the third vector from my independent set, right, A3, the negative 1, 0, 0, 0, and I subtract the projection of A3 onto B2 and B1, right, the previous two, the vectors I found in the orthogonal set previously. So minus the projection of A3 onto B1, and also minus the projection of A3 onto B2. Alright, so again, A3 was that third column of the matrix, negative 1, 0, 0, 0. Minus, now projecting onto B1 will just give me a scalar multiple of B1. So some multiple of 1, 1, 1, 1. And what's the scalar? The numerator will be A3 dotted with B1. Well, that's just negative 1 for the numerator. And B1 with itself, the dot product is 4. So I have plus 1/4 of these. Then we have minus and then a projection of A3 onto B2. Just give me a scalar multiple of B2. Now B2 is this vector here, the negative 1, 1, 1, negative 1. Alright, so what's the dot product of A3 with B2? So A3 with B2, that'd be 1 plus a bunch of zeros. So just 1 in the numerator of the scalar. And the denominator is the dot product of B2 with itself. So again, 4. Alright, and let's put these together. And we're getting our third vector, right, B3. The first components, you have negative 1, then plus a fourth, plus another fourth. So that's negative 1 plus a half. It's negative half. Right, negative 1 plus 1/4 plus 1/4. Alright, then we have 0 plus a fourth minus a fourth. So 0. Then 0 plus a fourth minus a fourth again. So 0 again. And then 0 plus 1/4 plus another fourth. That's 2/4, that's 1/2. Alright, and if you'd like, I'll pull the half out of this. This is half of the vector negative 1, 0, 0, 1. Alright, and you can double check, this vector is orthogonal to B1. Alright, do the dot product of 1, 1, 1, 1 and negative 1, 0, 0, 1. You get 0. And B3 is also orthogonal to B2. Alright, take the dot product of negative 1, 1, 1, negative 1, and negative 1, 0, 0, 1, and you'd get 0. And we already showed earlier B1 and B2 are orthogonal, so we do have an orthogonal set, alright, with B1, B2, and now this B3. Now let's normalize them. And I'll get an orthonormal set that I'll use as the columns of matrix Q. Alright, so B1. The norm of B1 is 2. Alright, it'd be the square root of 4, the square root of the dot product with itself. Alright, of B1 with itself, which was 4. Square root of 4 is 2. So I just divide each component by 2. So I got a half, a half, a half, and a half. Right, there's a unit vector in R4. B2 also has a norm of 2, right? The square root of 4. So I divide each of those by 2 and get negative half, 1/2, 1/2, negative half. Negative half, 1/2, 1/2, negative half. All right. And then really, I don't need the half here, right? What the norm of this vector, negative 1, 0, 0, 1, is the square root of 2. Let's divide this vector by the square root of 2. All right, and we'll get a unit vector. So negative 1 over the square root of 2, 0, 0, and then 1 over the square root of 2. And here we have it. All right, here is an orthonormal set of vectors, right? Again, take any pair of them, they'll be orthogonal, and they are all unit vectors in R4. The dot product of each one of those with itself is 1. All right, so I've got my matrix Q, right? That matrix with this, it's got the same size as A. It's going to be a 4x3 matrix, but with orthonormal columns. All right, so matrix Q is this matrix with these as columns, right? So with a half, 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 negative 1 half, 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 negative 1 half, and negative 1 over the square root of 2, 0, 0, and positive 1 over the square root of 2. All right, there's Q. All right, there's Q. And then R, all right, that upper triangular matrix, remember, will be Q transpose times A. All right, so Q transpose is a 3x4. With half, negative 1 half, negative 1 over the square root of 2, half, half, 0, half, half, 0, and a half, negative half, 1 over the square root of 2. Times A, right, now matrix A, going back here again, was this 4x3. Looks like there's a lot of zeros in there, so this shouldn't be so bad to do by hand. All right, so we have a 3x4 times a 4x3. It's going to be a 3x3. And this, if I did everything right, this matrix R should be upper triangular. All right, so the first row, first column is, a half plus a half plus a half plus a half. So 4 halves, or 2. The first row, second column is 0 plus 1 plus 1 plus 0. It's also 2. The first row, third column is just negative half. All right. Then the second row, first column, again, should be 0, right? This is, and look at this, it's negative half plus a half plus a half plus negative half. That is indeed 0, like I want, right? Every value below the main diagonal should be 0 if this is to be upper triangular. Then the second row, second column, 0 plus 1 plus 1 plus 0, so that's 2 again. Then second row, third column, just positive half. All right, and then these should be 0. Right, let's check it. You got negative 1 over root 2 plus 0 plus 0 plus 1 over root 2. Nothing. Right. And then third row, second column, 0 plus 0 plus 0 plus 0, 0. And then third row, third column, you have positive 1 over the square root of 2. So here's my Q, right, this matrix with orthonormal columns. Here's my R, this upper triangular matrix. And the product of Q and R should be A, should be, right, this matrix here with this 4x3. And again, I'll just verify that on my calculator. Right? So off to the side again, I'll always double check your work. Right? Verify that A is indeed equal to Q times R. Right? We do have the Qr factorization of A. Right, so pause it and be back really quick. Right? All right, and we're back. And as I mentioned, I entered my matrix. My matrix A is Q. I entered this matrix Q, this 4x3. with the orthonormal columns. Now on the calculator, my matrix B is this 3 by 3 matrix R, this upper triangular matrix. I entered these as is, and you see when you multiply Q by R, or on my calculator A by B, I'm getting this matrix 1, 0, negative 1, 1, 2, 0, 1, 2, 0, 1, 0, 0. That is, see, matrix A. So A is indeed, Q times R, this matrix with orthonormal columns times this upper triangular matrix. All right. So that's it. Some demonstrations of how to take an M by N matrix and express it as a product of Q and R, right? A matrix with orthonormal columns and an upper triangular matrix. Just remember, I want to start off with a matrix that has independent columns. All right. If the matrix doesn't have independent columns, not gonna really go into talk about the Qr factorization. So start off with a matrix with independent columns, then take that set of independent columns, go through the Gram-Schmidt process or some other procedure. There's other ones out there to help you orthonormalize a set, but I went through the Gram-Schmidt process here to construct an orthonormal set of vectors, made those the columns of my matrix Q, then multiplied Q transpose by A, right? Q transpose times A, and that gave me an upper triangular matrix R, such that A was equal to Q times R. Great. All right, so hopefully these examples were reasonably easy to follow, and hope you enjoy practicing your own problems. Finding your own QR factorizations for any given matrix, as long as the columns of that matrix are independent. And thank you very much for watching.